In 1859, the sun unleashed a storm so powerful it set telegraph lines ablaze and made the night sky glow like midday. In 2012, we missed something even bigger by 9 days. And statistically, it's no longer a matter of if, only when. Those were storms within the range of recorded history. But when astronomers look at stars like ours, they've observed eruptions far more violent than anything humanity has ever recorded. Not slightly stronger, orders of magnitude stronger. And here's the unsettling truth. Nothing in stellar physics guarantees that our sun could never do the same. But before we go there, we need to understand what happened in 1859. On September 1st, 1859, an English astronomer named Richard Carrington was sketching sunspots when he saw something extraordinary. A sudden flash of white light burst from the surface of the sun. It lasted only minutes. Within hours, Earth began to respond. Telegraph operators across Europe and North America reported violent surges of electricity racing through their lines. Sparks leapt from telegraph equipment. In some offices, the paper on operators' desks ignited. Some operators received electric shocks. In some cases, messages continued transmitting even after power supplies were disconnected. The storm itself was driving the current. That night, the sky turned an ominous red. Auroras rippled across regions that had rarely, if ever, seen them before, visible in Texas, Hawaii, and even Rome. In parts of the United States, the sky was bright enough to read a newspaper at midnight. This was not a distant astronomical curiosity. It was the sun interacting directly with human technology. And in 1859, our technology was primitive. So what actually happened? The sun's surface is a chaos of magnetic fields, twisting, stretching, and tangling over time. When those magnetic lines suddenly snap and reconnect, they release extraordinary amounts of energy. Sometimes that energy is accompanied by a vast cloud of charged particles, hurled outward into space at millions of kilometers per hour. If Earth happens to be in the path of that cloud, it collides with our planet's magnetic field. Most of the time, our magnetosphere absorbs the blow, but in extreme events, it doesn't just glow in the sky, it induces powerful electrical currents in long conductors below. Power lines, railways, pipelines. In 1859, that meant sparks and auroras, but for most people, it was a beautiful spectacle in the sky. Today, it would mean something far more complicated and far more serious. In July 2012, the Sun launched a massive coronal mass ejection, a cloud of magnetized plasma weighing billions of tons. It tore through space at more than 2,000 kilometers per second, fast enough to cross the distance from the Sun to Earth in less than a day. 4 days earlier, Earth had been in its path, but the planet had already moved on in its orbit. The storm passed through the exact region of space we had just occupied. We weren't in its path. NASA's Stereo spacecraft recorded the blast as it swept past, measuring an event comparable in strength to the Carrington storm of 1859, possibly stronger. Had the timing been slightly different, it could have struck a world now dependent on satellites, GPS, high-voltage transformers, and globally synchronized networks. Researchers later described it as a near miss, and that's exactly what it was. We were lucky. But luck is not a mitigation strategy. It's tempting to assume events like this are rare anomalies, that our sun is simply not that kind of star. And in some ways, that's true. The Sun is a G-type main sequence star, one of billions in our galaxy. When NASA's Kepler mission monitored thousands of similar G-type stars, astronomers were able to compare their brightness variations and magnetic activity. Many younger, faster rotating G-type stars were far more volatile than ours. By comparison, the Sun appears relatively stable. It does not routinely unleash the most violent stellar eruptions observed elsewhere in the galaxy. But that reassurance rests on a surprisingly thin foundation. Kepler observed those stars for only a few years. We have been monitoring our own star in high resolution for only a few decades. Electrical civilization has existed for barely a century and a half. A star's magnetic behavior unfolds over thousands, sometimes millions of years. We are trying to define the upper limits of a 4 billion-year-old system using a fragment of data. It would be like studying a volcano for a week and concluding it will never erupt. The Sun may be calm, but calm does not mean incapable. And nothing in stellar physics guarantees permanent restraint. We've been talking about the worst solar storms in recorded history. There is a class of solar eruption that makes the Carrington Event look modest. When astronomers turned their telescopes towards stars like ours, they found something unexpected. Eruptions releasing energy equivalent to billions of nuclear bombs detonating at once, in a single burst. Not over days, not gradually, in minutes. These events even have a name. Astronomers call them superflares. Some of these eruptions are thousands of times more energetic than the Carrington storm of 1859. They have been observed on G-type stars, remarkably similar to our own. For a long time, we hoped our Sun was the exception, that these were monsters that only lived elsewhere. But we were looking in the wrong place. We didn't need a telescope to find them. We needed a microscope. Inside the rings of ancient cedar and pine trees, scientists discovered a biological black box. They found massive, sudden spikes in carbon-14, chemical scars left behind by high-energy cosmic radiation. These are known as Miyake events. The most famous occurred in the year 774 AD. It wasn't a Carrington event, it was something much larger, up to 10 times more powerful. It proves that superflares aren't just an astronomical theory, they have happened here, to us. Now, here is the important part. Our Sun does not appear to produce these regularly. It rotates more slowly than many of the most active stars. Younger stars rotate rapidly, and that motion drives a stronger magnetic dynamo deep within the star, twisting and amplifying magnetic fields. Our Sun, by contrast, rotates more slowly. Over billions of years, it has shed angular momentum, gradually calming its magnetic activity. That slower rotation is one reason it appears less volatile than many of the flaring stars observed by Kepler. It is, by stellar standards, magnetically calmer. But our observational window is short, and nothing in stellar physics guarantees we've already seen the upper limit. And that fact, as we're about to discover, is unsettling to say the least. Even if our Sun never produces something that extreme, a Carrington-scale storm is well within its demonstrated range. So what would happen if one hit today? The impact would not be uniform. The side of Earth facing the Sun would take the initial compression of the magnetosphere, but the real danger wouldn't stay there. As Earth's magnetic field shifted and reconfigured, powerful electrical currents would be induced across the planet, particularly in mid to high latitude regions. Not evenly, not everywhere, but in enough places to matter. The greatest risk isn't your phone, it's the power grid. High-voltage transformers are enormous, custom-built machines, some weighing hundreds of tons. They are not sitting in storage warehouses ready to be swapped out. If a severe geomagnetic storm damaged dozens of these units across multiple regions simultaneously, recovery would not be immediate. Manufacturing replacements can take months. Transporting and installing them takes longer. Power would return in stages, but some regions could face prolonged outages, not days, but potentially weeks, even months in worst-case scenarios. And without stable power, other systems begin to strain. Satellites exposed to intense radiation may degrade or fail. Low Earth orbit satellites could experience increased atmospheric drag. Navigation systems might falter. But the deeper vulnerability is timing. Modern financial networks, cellular towers, and data centers rely on precise GPS time signals to stay synchronized. If those signals become unreliable, systems don't collapse instantly, they destabilize. Trades cannot be timestamped correctly. Cellular networks lose synchronization. Internet routing becomes congested as traffic is rerouted around damaged infrastructure. The internet is resilient, but it still depends on power, timing, and physical infrastructure. If large power regions go offline, data centers go offline. Traffic shifts. Bottlenecks form. Recovery becomes uneven. Hospitals rely on generators. Water treatment plants rely on electricity. Fuel distribution relies on coordinated supply chains. This would not be the end of civilization, but it would be a sudden, violent collision with the reality of our just-in-time world. In our modern era, most cities hold only a few days' worth of food and essential supplies. Those supplies move on networks governed by the very satellites and digital protocols that a superstorm targets. When the taps stop running because the pumps have no power, and the shelves don't restock because the logistics networks are blind, the veneer of stability thins very quickly. The danger of a Carrington-scale event isn't just the darkness, it's the friction. It's the breakdown of the invisible trust we place in a globalized system that was never designed to operate without a pulse. This would be disruption on a scale we have never experienced. Not because the sun is uniquely violent, but because our infrastructure is uniquely interconnected. All of this sounds bleak. But we are not completely powerless in the face of this. Space weather monitoring has improved dramatically over the past few decades. Satellites like SOHO, SDO, and DSCOVR monitor solar activity in real time, giving grid operators hours, sometimes days, of warning before a major geomagnetic storm arrives. Power companies can temporarily reduce load. They can disconnect vulnerable transformers. Some infrastructure can be hardened against induced currents. New designs are being studied. Emergency planning exists. The problem is not ignorance, it is priority. Preparing for rare, high-impact events is expensive, and the quieter the sun appears, the easier it is to assume the risk is distant. Until it isn't. In 1859, we didn't have satellites. In 2012, we were lucky. We have built a civilization that depends on invisible systems, orbiting above us and stretching across continents. And all of it exists beneath a star that still behaves like a star. The sun is stable, until it isn't. It's no longer a matter of if, only when.